Hello everyone, myself Deepshika V from the Department of Computer Science and Engineering, SIC Bangalore. In today's video, we'll be seeing how to generate the object code for the given SIC/XC source program. Now let's quickly jump into the video. Generate the object code for the following SIC/XC source program. Also write the object program, that is write the header record, text record and end record. So here we have the program given to us, that is the SIC/XC program, and we also have the mnemonics and opcode given to us. Using this data we have to generate the object code, and then we have to also write the object program. So first let's see how to generate the object code. To generate the object code, we have to first make 5 columns. The first column is for the location counter, the second for the label, third for the opcode, fourth for the operand, and fifth for the object code. Now first we have to find the location counters for each and every instruction. We know that in SIC/XC architecture there are totally 4 formats of instruction. Format 1 can have 1 byte of memory. Format 2 can have 2 bytes of memory. Format 3 can have 3 bytes of memory, and Format 4 can have 4 bytes of memory. Using this information, we can find out the location counters for every instruction. Now first we have sum start 3000. Now sum is the name of the program. Start 3000. This is the starting address of the program. So this 3000 will be the location counter for this instruction. Next we have first clear X. X is a register. So whenever there's a register involved in the instruction, it will be format 2 instruction. So format 2 can have 2 bytes of memory. Now what we have to do is we take the first starting address of the memory, that is 3000 plus 2 bytes. We get 3002. So that will be the location counter of the third instruction. The next instruction is LDA #0. So this cannot be a format 2 instruction because there is no register present, and if there is a plus sign before the instruction, then only it is a format 4 instruction. Since there is no register or a plus sign, this instruction is a format 3 type instruction. So for format 3, it is 3 bytes. For this location counter, we add plus 3. That is 3002 plus 3. We get 3005. So that will be the location counter of the next instruction. The next instruction is plus LDB #total. So since there's a plus sign present before the instruction, it is a format 4 instruction. For format 4 type instruction, it is 4 bytes. So we add 4 to the location counter. That is 3005 plus 4, you get 3009. So the next instruction is base total. Base is a assembler directive and it will not be having any location counter. So we write 3009 for the next instruction after base. So the next instruction is loop add table X. Here there is no register or there is no plus sign present before the instruction. Hence it is a format 3 instruction. So we add 3 bytes. That is 3009 plus 3, you get 300C. That will be the location counter of the next instruction. Next we have TIX count. Again it is format 3, so plus 3 bytes. That is 300C plus 3, 300F. That will be the location counter. Next we have JLT loop, again format 3. So 300F plus 3, you get 3012. Next you have STA total, again format 3, so plus 3. 3012 plus 3, you get 3015. The next instruction is count reserve word 1. We know that one word equals 3 bytes. So we add 3 to the location counter. That is 3015 plus 3, you get 3018. That will be the location counter of the next instruction. Next we have table reserve word 2000. So 2000 words are being reserved under the name table. So 2000 words equals 6000 bytes. 6000 is in the decimal form. When you convert 6000 to hexadecimal, you will get 1770. We have to add this hexadecimal number to the location counter. That is 3018 plus 1770. You will be getting 4788. So that will be the location counter of the next instruction. Next you have total reserve word 1. So again one word equals 3 bytes, add 3. 4788 plus 3 you get 478b. So this will be the location counter of the last instruction. Now once we have found out the location counters for all the instructions, we can now generate the object code. So the first instruction is clear X. So this is the format 2 type of instruction. So for format 2, the first 8 bits will contain the opcode, the next 4 bits will contain the first register, and the last 4 bits will contain the second register. So in the question we have certain mnemonics and opcode given. I have presented it at the top of the screen. So for clear it is B4. B4 is in hexadecimal form. When you convert it to binary you get 1011 and 0100. So this will be the opcode for this instruction. Next we have the register as X. So we know in SIC XE architecture the number for X is 1. So this 1 we'll represent it in a 4-bit format, and that we'll be writing it in the first register. Next we have only one register, so the second register will just be 0. To generate the object code for this instruction, what we'll be doing is we'll be grouping this into 4 bits. So now 1011 is nothing but B, 0100 is 4, and 0001 is 1, and this will be 0. So now this will be the object code for this instruction. The next instruction is LDA has 0. So this is a format 3 type of instruction. So for format 3, the first 6 bits is the opcode, and then we have 6 flags, that is NIX BPE. N stands for direct addressing mode, I stands for immediate addressing mode, X stands for indexed addressing mode, B stands for base relative addressing mode, P stands for program counter relative addressing mode. And this E bit is used to differentiate between format 3 and format 4. So E equals 0 for format 3 and E equals 1 for format 4. And then we have 12 bits for the displacement field. Now the instruction is LDA. So the mnemonic for LDA is 00. So when you write 00 in the binary format, you will have 8 zeros. Converting this to the most significant 6 bit, you can write 6 zeros in the opcode. Now since there's a hash present in the instruction, you can tell that it is an immediate addressing mode. So the I flag is set to 1. Now to write the object code, again you have to group them into 4 bits. So the first 4 zeros will be 0. Next you have 0001. This will be 1. And the next 4 will be 0. Then the displacement field will have 3 zeros here. So now this will be the object code. The next instruction is plus LDB hash total. So since plus is present, it is a format 4 type of instruction. So this format is same as format 3, but instead of the displacement field, we have the address field, and it contains 20 bits. Now the opcode for LDB is 68. Now when we convert this 68 into binary form, you get this value. Now taking the more significant 6 bit, we write it in the opcode. Then since hash is present in the instruction, you can tell that it is of immediate addressing mode. So the I flag is set to 1. And since this is a format 4 type of instruction, E is also set to 1. Now to write the object code, we again group the values into 4 bits. So 0110 is 6, 1001 is 9, 0001 is 1, and this will be written as it is. So now this will be the object code for this instruction. So the next instruction is add table comma x. So the opcode for add is 18. 18 should be converted to the binary form, and the first significant 6 bits will be written in the opcode. Next, by comma x, we can tell that it is having a indexed addressing mode. So the flag for x is set to 1. Now this is neither direct addressing mode nor immediate addressing mode, so the flags for n and I are also set to 1. Now we have to find out if it is a base relative or program counter relative addressing mode. For E, we can tell that since it is format 3, it is 0. So to find out if it is base or PC relative, we have to first calculate the displacement. So to calculate the displacement, we have to take the location counter of table, that is 3018, and subtract it with the count location counter, that is 300C. So on subtraction, you will be getting 12. So 12 is present in the range of minus 2048 to 2047. So this should be present in this range for it to be a program counter relative addressing mode. So the flag for P is set to 1 and B is set to 0. Now converting 12 to hexadecimal, you will be getting C. Write it in the 3-bit format, you will be getting 000C. Now to write the object code, again you have to group them into 4 bits. So this will be 0001, that is 1, 1011, that is B, 0010 A, and this will be 00C. So this will be the object code. So the next instruction is TIX count. The opcode for TIX is 2C. Converting it into binary form, you'll be getting this value, and you have to write the first significant 6-bit in the opcode. Next, you can, by looking at the instruction, you can tell that it is neither direct nor immediate addressing. So those flags are set to 1. Next, it is also not index addressing mode, so the flag for x is set to 0. Now we have to find out if it is base or PC relative. Now since this is a format 3 instruction, E is set to 0. Now to find the displacement, we have to take the location counter of count, that is 3015, and subtract it with the location of the next instruction, that is 300F. So on subtraction, you will be getting 6, and this is in the range of the PC relative. Hence this is a program counter relative addressing mode. So the flag for P is set to 1 and B is set to 0. Now again grouping them into 4 bits. 0010 is 2, 1111 is F, 0010 is again 2, and this is 006. So this will be the object code for this. Next we have JLT loop. The opcode for JLT is 38. Convert it into binary form and write the most significant 6-bit in the opcode. Next, this is neither direct nor immediate addressing mode, so N and I flags are set to 1, and it is neither index, so X is set to 0. Now to find out if it is a base or PC relative, I have to calculate the displacement. So for JLT loop, the location counter of loop is 3009, and the location counter of the next instruction is 3012. So on subtraction, you will be getting -9, and this is present in the range of the PC relative. So hence this is a program counter relative addressing mode. So P is set to 1 and B is set to 0. Now on converting -9 to the hexadecimal form, you will be getting FF7. So this will be the displacement. Now again grouping them into 4 bits. 0011 is 3, 1011 is B, 0010 is 2, and then FF7. So this is the object code for this. So the next instruction is STA total. So the opcode for STA is 0C. On converting it into binary, you'll be getting this value, and you have to write the first significant 6 bits in the opcode. So by looking at the instruction, we can tell that it is neither having a direct addressing mode nor a immediate addressing mode. So the flags of N and I are set to 1, and it is neither having index addressing mode, so X is also set to 0. To find out if it is base or PC relative, we have to calculate the displacement. So the location counter for total is 4788 minus the location counter of the next instruction, that is 3015. On subtraction, you will be getting 1773 in the hexadecimal form. On converting it into decimal, you will be getting 6006. So this value is not present in the PC relative range. Hence, this is not having a PC relative addressing mode. So the flag for P is set to 0 and B is set to 1. Now we have to calculate the displacement again. So to calculate the displacement, the location counter of total is 4788 minus the location counter of base. So base is also having total, and again total is having 4788. So 4788 minus 4788, you will be getting 0. So the displacement is 0, 0, 0. Now to write the object code, group them into 4 bits. So 0, 0, 0 is 0, and then 1, 1, 1, 1 is F, then 0, 1, 0, 0 is 4, and this is 0, 0, 0. So this will be the object code. Now next, the count reserve words do not have any object codes, and end also doesn't have any object code, but the starting address of the program can be written in the object code. So here it will be 3000. So once we derive the object code, we'll try to generate the object program. So the object program has 3 sections. So the first section is the header record, the second section is the text record, and the third section is the end record. So the first section starts with the letter H. Then you have 6 columns for the name of the program. So the name is sum here. After writing sum, the next 3 columns are left blank. Then we have to write the starting address of the program, that is 3000. So since even for this 6 columns are allocated, another 2 zeros are added to fill up the space. Then we have to write the length of the program. So to calculate the length of the program, the address of the last instruction is subtracted with the address of the first instruction. So on subtraction, you'll be getting 178B. So that is the length of the program. Next, on moving on to the next section, that is the text record. It starts with the letter T. Then we have the starting address of the program, that is 3000 in 6 columns. Then how we will get 15 we'll be seeing in a while. So after that, we'll be writing the object codes of all the instructions. So after writing the object codes, on counting the number of columns, you'll be getting 42 columns. So 2 columns equals 1 byte. 42 columns will be equal to 21 bytes. So 21 is in the decimal form. In converting it into the hexa form, you'll be getting 15. So that's how you get 15 here. So then the next section is the end record. So it starts with the letter E, and then the opcode for end is 3000, that is written in 6 columns. So now this is the object program. So here we have both the object codes and object program derived successfully. Thank you.